Okay, we should be live right now.
Okay.
Excellent connection. Okay, we're good. Okay, so today we wanted just to have a free-form chat with some questions that Tobias had on computability, provability, the relationship with experimental verification, and the thing that we are trying to basically do in the project. So, Tobias, go up.
Yeah, so it's just that last week, um, this guy introduced, his project about including physics into a proof checker.
Mhm,
So, and then to me, this like opened up like connections to like just verifiability in the first place. And then I was just recently wondering about computability, actually, because I just realized that in my math course, the professor really hates calculating stuff. And I just noticed like, to a physicist, this is like really foreign because if I cannot calculate it, like what am I even doing?
mhm,
I have to be able to calculate things to connect them to predictions somehow. It's totally normal to me. I was just curious, like how fundamental is that? Is it just a bias, that's what we're used to? Or how serious do we want to take the fact that we basically always compute stuff somehow? And so then this guy last week was kind of related. And
mhm.
then Mark is usually talking about things like constructive logical foundations and stuff like this. So that's why I just noticed to me somehow this is related, but it's like different approaches. I have a book I found it in the library, which talks about computability of certain things, namely like operators on Hilbert spaces, like can I compute the eigenvalues and stuff like this.
Mhm.
Um, and their approach is basically also within normal classical mathematics, where you can just use normal analysis and so on to prove whether something is computable or not, once you define what you mean by that. Um, but they mentioned, for example, in the preface that this might be not like unnatural to use classical mathematics in this context because most people would put this in the first place some other axiomatic system, I guess. So I see there are multiple approaches to a somewhat the same question. I
Yeah.
just don't understand what is actually the precise question that we want to address. What is the physical problem? And if we have these different approaches from different angles, what are the benefits? Are there things that I actually cannot do without this stuff? Like, do I really want to like start from like throw out the axiom of choice or whatever? That's something easy I understand. Or do I just want to use it and I can prove stuff? But whenever it gets mapped to physics, I just have computable things or something like this?
Mhm.
Um, so I don't know where to make the trade-offs or whether one of the approaches is really like how much freedom do we have in our approach? Can I always do it in like um use normal mathematics and just check later that it's computable? Do we want to do that? It's a bit like I don't know. Do we want to it feels like Mark always tries to do everything. And so if I use a programming analogy, it will be like he wants to do everything in assembly. And I'm like, I just know Python. Look, it's I'm kind of afraid to go that deep.
Yeah.
Does it
So
make sense?
I've been thinking and been struggling with some of these things myself. I formed, let's say, some opinions, which I don't know whether there is the sort of the correct way to look at everything, but but it sort of has been validated by when was talking to different people because different people care about different things. So the people, let's say in standard mathematics, the one that are not constructivists, that accept axiom of choice and so on, they're typically interested in what can be proven. And a proof is essentially a type of computation, or a computation is a type of proof, whatever you want to say it. But because
Yeah.
at the end of the day, in both cases, you have a set of starting points, and then you have some logical step within some type of pseudo-formal system, and then you arrive to a result that follows from. And whether you're doing a proof, or whether you are doing putting a number and then doing some number calculation. That's the same thing. It's just the type of steps that you're using that are different. And so the people who accept axiom-Strauss in standard mathematical series is you basically are saying, I just care about what I can prove. And uh, um, and then there is the whole thing of proof theory that tells you sort of the domain of what can be proven in certain contexts and so on. And again, the issue is that a proof at the end of the day has to be complete, has to be writable, let's say, expressible in finitely many steps. Now, if you're doing standard mathematics, there are some types of stacks that involve, in principle, infinite steps that then you can collapse it to one step and then proceed forward, right? And so the axiom of choice, you can think it as doing something like that, because so when you invoke the axiom of choice, it's like you're invoking the existence of a function that it's typically not expressible in finitely many steps. So you have something like the well ordering of the reals. The well ordering of the reals is essentially a way to take the reals and put them in an order such that you always have an immediate successor. Right? So in the reals, you never have an immediate successor with the standard ordering. But again, if you accept the axiom of choice, you can always sort of put all the items in a set in a line. And what happens is that you're basically going to, keep counting one after the other. At some point, you have some type of infinity, and then from that infinity, you reset. That's sort of how the well ordering works. But the point is that if you can, in principle, have a well ordering of the real, it's just that it's not expressible in finitely many symbols. Like you really can't. And so when you invoke the axiom of choice, you basically say, okay, I will invoke the existence of this thing that I can't write, but I say that it exists and so on. And so a lot of the time, that's what you do in standard mathematics. You have something that in principle takes infinitely many amounts of steps or infinitely many symbols to describe it. You say, okay, this exists, and I'll contract it in one step, and I'm done. And then a constructivist basically say, well, this is nonsense because I don't have actually that thing. And so if I want to compute actually elements, I can't make that step. At least, again, this is my understanding of the thing. And if there is somebody in the chat that has a better understanding, or somebody wants to write later in the comment with a better understanding, this is my understanding. A constructivist would basically say, well, I can't do that. That makes no sense. When I actually write calculation, I can't do that. As I want to make sure that all my starting points are definable, and you can write them down with finitely many symbols, so that those are the things that I actually can talk about. And so when you compute, then you're going to have a proof that it's made of finitely many steps, that you can actually go and manipulate these initial things, and you get a final result, and therefore you're guaranteed that the result can be computable and so on. And this means that you have to sacrifice some of the standard techniques, but then you're guaranteed that you can do this. Now, the issue is that when we define physical objects, we do neither of those things. Because if I want to define that there is a mass of the electron and I can go and measure it and it's a particular value, there is no sense that that thing is computable. Like I'm not computing it. It's something that it's there, and I go and make a measurement, right? And And so you have to postulate that there is something in the real world that you can go and measure. And then, yes, a particular measurement can only be done in infinite time, infinitely many steps, and is going to give you finite precision. But if you want to describe the thing that you're measuring, you have to be able to allow the full extent of whatever you're going to get in the limit, because if you can say, if you basically say, oh, I can always make my measurement more and more precise and more precise, if you're writing a law, a physical law that depends on the fact that there is a mass and the fact that there is a particle that has a mass and so on, the law has to be described on at all level of precision. And then if you want to describe it at all level of precision, then you have to make sure that the map works for every finite, arbitrary finite size, which means you have to be able to take the limit. And so to me, physics sort of stands a little bit in between, because again, the whole purpose is what is the subject matter that you're describing? Like if you're describing things that I can fully formalize and fully calculate on, you have one thing. If you basically say, no, I'm just going to see what I can prove in the abstract, that you get some other thing. And then if you say, well, I want to describe the objects that I can define experimentally, to me, you get another thing.
So when it comes to predictions, I can only predict, which I would say is calculate, that it will be inside some open set, but you want to define all the possibilities, as you call them, right?
Right.
And then you need whatever you can get in the lab. And then you say it's much more, it's bigger, it's like you need the whole real line. So the possibilities are the points that you want to include, even though they don't correspond to the experimentally verifiable statements.
Right, because you will need to be. So let's put it like this. A simple case. You have an initial position and a final position and a process that links the initial position to the final position. Okay, so you have a map. And then you want to say, does that map has to be computable? Well, it's it's the physics, it's nature that it's implementing that map. Whether I can compute it with finitely many symbols and so on a computer, it's sort of it doesn't matter, because as long as nature can actually implement that map, and I can recognize that there is, up a certain level of precision, I reckon could distinguish that map from other maps, then I'm good. Now, you say, can I compute it? Well, one, I might not be able to compute it, but two, I might not even be able to know exactly what the map that nature is doing in that specific case actually doing, because I'll never know the map with infinite precision anyway. So in principle, you would not only say that I have an open interval of the initial and the final, an open set for the initial and the final values that you are going to measure in, you're going to have also an open set on the map, because you don't know exactly what map is there. So I don't know how to make computation of open set over or an open set of maps. Like I have no idea whether that makes. But sort of there is a. So worrying that the function that I write down as the map from the past to the future is actually computable and so on, it seems to me that you are. Can I say, forgetting that you have much bigger problem to begin with. And the issue there is always that whenever you are writing these maps, at the end of the day, you're writing a model of what you are actually working on. So it's not really that you have um, it's not really that your map actually represent something that exists exactly like that map. It's still an idealization of what is there to begin with. So I'm not even so sure if you're requiring that model to be computable, if you're actually making a statement about what are the possible maps that exist there, or whether you just want to find, since you can't tell exactly which map you're gonna have, you're gonna find one that is more convenient, that is close enough, and is convenient to calculate.
Um, so so I'm thinking whether there could be the situation where I cannot compute, let's say, the final state. Like I'm given an initial state, the function that maps to the final state. It's not computable,
Mhm.
but whatever the state is and how I define it, I can experimentally somehow identify it. So would it be enough that if I am given the final state, I can check whether this is, so I define, still the function is defined. I cannot compute it. Can I check that if I'm given the answer, it was the right one, right? That
Correct.
would be enough.
Yeah.
Okay. That would still be, it's kind of bad because it's not predicting, really. I mean, I was settled in the first place on what the function is, so I defined what the right answer is, but it's kind of abstract,
Yeah.
pure like, but that would still be science, I guess.
Yeah. So if I remember correctly, there is an example in solid state physics that there are some property of materials that you basically cannot compute whether a particular material has that particular property.
I saw an article that claims there are uncomputable things in physics.
Yeah.
I didn't read the whole thing, but I like an article summarizing it. It was a bit of a popular article, but like um I think I know what you're talking about, but I thought this was only like for idealized infinite systems. Um, so I'm not sure how physical
So the,
this
the, the case that
result
I
is.
read, I did read the paper, it was like 3 years ago or more, and I don't retain all the details, but it was roughly that you had, I don't remember if the Lagrange or anyway, some description of the material, and a theoretical description of the material, and then you basically had a question whether the material had a particular property, and they even went through they basically created a proof that showed that you wouldn't be able to calculate the answer.
Mhm.
Now, I didn't understand enough to understand exactly what the cause was, because the proof, it was like, I don't know, 20 pages. Like it was far too complicated for me to follow. And I do not know whether there is a sort of a general rule that you could, but in any case, you're right that if there is something that is non-computable, there has to be something that has to do with an infinity inside, right? Because if everything is finite, and the description is all finite, and the map is mapping
Yeah.
only from finite thing to finite thing, of course it's gonna be computable. It's not. At
Mm.
least in principle, then it could still be
Yeah, yeah.
practically completely incomputable. But yeah. So yeah. At the worst, if you have a map that that goes to a finite space, you can just enumerate all the possible
Yeah.
cases, right? And you can always do that. So I mean, again, in principle, you can always do that.
Yeah. Um, by the way, when you talked about the infinite precision, um, I was wondering again. Also, the rational numbers are like, dense. I
Yeah.
can always go finer and finer. It is just the topological
Yeah.
statement. I want to have all the limits.
Right. So the issue is that as soon as you put in a topology and you want the closure on the open sets, you're essentially going to get the limits,
Yeah.
right? Because you take, let's say, all the open interval from x to infinity, where x is greater than pi.
Mhm.
And then now you take the union of all of those, you get the set from pi to infinity, like the open interval from pi to infinity.
Yeah.
So
Yeah.
that's kind of why, uh, like, unless you really know that you come from a ratio, right? So you have, number of chicken over number of people, right? Those are integers and you divide them and so on, right? But then it depends how you're measuring the quantity. Like if you're measuring it because you're measuring the denominator and the numerator and the denominator, then the topology is actually going to be the discrete topology at that point, because you can verify, exactly which rational number you have.
Mm.
But if you are measuring the ratio because you have some other technique, like I don't know, let's say that you have some what could be a good example? Like you have a mixture. Yeah, you have a mixture of materials, right? So you know that in principle there are atoms, right? So on. But then when you measure it, you're just measuring some type of ratio between the mass of the total mass of one versus total mass of the other. You're going to have some finite precision on that mass. And now the type of topology that you use for that corresponds to that measurement is going to be the order topology. So the open intervals of
Okay.
and that's it. So it's how you measure it is going to tell you which topology you have.
Okay. So it seems like we want these types of objects, like we explicitly want the points on the real line, even though we will only talk about open sets afterwards.
Yeah.
So that's just why my intuition was that we want to kind of stay somewhat in classical mathematics, and then use tools like we can check whether some functions are computable or not if necessary. Um, and of course, checking that our proofs just work by a proof checker is always nice, just to be sure. But then um, is this like convenient to make sure we stay within physics, or I don't know. So
So let me go back to the issue whether we can still be constructive or not, and that's the part that I basically don't know. I would need to talk to somebody who understands these details better. The the whole point is that at the end of the day, the what we have in physics, when we do theoretical physics, we should have idealizations of experimental procedures. And so one of the things that we have in the whole thing of experimental domain and experimental verifiability, we require that we have verifiable statements that have an experimental procedure to test whether the statement is true. And we can only run up to countably many. And the countably many tests represents the fact that you can start and maybe conclude finitely many over an arbitrary long time, so that you can always start a new one and test something new. This means that not only we have countably many statements, but we have an enumeration. Like we know a particular order of how to get one after the other. And the order, the fact that this infinity is ordered, I think, my understanding is very important because whenever you deal with infinity, reorderings completely changes the nature of infinity. And one of the simple example that I have, if you imagine that you have a sequence of 1, 0, 1, 0, 1, 0, 1, 0, you would want to be able to say that you get the 1 50% of the time. But now you can take, you can reorder your 1, 0, 1, 0, 1, 0 when taking the first one, the second one, and the first 0. And then you take the third one, the fourth one, and second 0. And so now you reorder this thing, and now you have the sequence 1, 1, 0, 1, 1, 0, 1, 1, 0, and you would like to be able to say that now one has 66% of the time of coming out, right? So whenever you're doing even statistics, there is already a sense that the statistics is not just based on the fact that you have an infinite collection or all that, but the ordering matter. And from what I understand, when people do constructive mathematics, it's not enough to say, oh, something is countable. You need to have the way, the enumeration to go through that countable sequence, right? And so this is something that I struggle for a long time because again, I wanted to prove something. I wanted to understand whether I'm using axiom of choice or not. And it seemed to me that if I were able to say this is countable, well, if there is countable, I know that there exists an enumeration. I'm not using any choice. I get that enumeration and I do my things. So I'm not using the axiom of choice. So what's the issue? And then talking to somebody that understands these things more than me, he basically told me that constructive mathematics, yes, it doesn't want the axiom of choice, but it's not the only thing that it requires. And so the fact that when you have an infinity, then you have an enumeration has nothing to do with the axiom of choice, but it's still something that if you're doing constructive mathematics, you need to require. And so the point would be that whenever we have an infinity, because the infinity comes from an experimental procedure, we need a way to iterate that infinity. Because otherwise it's not physically defined. Because how am I, it's not enough to, because the infinity doesn't really exist in physics. It's the limit of I'm doing one thing after the other, and I'm giving an undetermined length of time, so I can always start something new. So that means I have an enumeration. And now the question is, even when we define the real numbers and we define the cuts and so on, we start with the verifiable statements. We start with some assumptions of these verifiable statements. And then we can say, okay, we can go and create these. We know that at the end of the day, we can think about these statements as collections of points, where the points are these limits of all the information that I can get in the infinite case, right? And so I don't know whether the type of construction that we already have are already something that are going to be very close or acceptable to people who do construction mathematics because you said, oh, okay, yeah, you know how to iterate these things and so on. Right.
Okay, so if you just have a countably finite sequence, the axiom of choice, I guess, would tell you there exists an enumeration. And if you don't have the axiom of choice, do you need to explicitly put another axiom that tells you that there exists this kind of function, which is a weaker axiom than the full axiom of choice?
So I think so. This is again where it's a
Yeah.
little bit over my head. So there are different weakening of the axiom of choice. So there is the axiom of countable choice. So there are like other things like
Okay.
this, right? In our case, what is my question is whether so we basically say, okay, we have a domain. A domain is countably generated, and we have the enumeration for that countable generation. So whenever I traverse my space, I have a standard way to do it. In fact, I'm only guaranteed that way to do it, right? I'm not guaranteed any other way. Right? And then the question is, well, now can I prove that any other infinite collection that I have can be traversable through that single
Mm,
iterative thing that I gave you? And that, if I understand correctly, and again, I might not, and if somebody
mm,
in the comments want to tell me how I'm wrong or wants to jump and tell me how I'm wrong in one of these sessions, I'd certainly be happy. But that's the thing that that I think might work. And then at that point, we basically have a hybrid in between. Because the people that are very, very adamant of rejecting completely the axiom of choice and everything, basically have everything finite, right? So basically, not even infinities, everything has to be finite and so on. Then you really have to remove the real numbers, and it's not even the problem that we are removing the real numbers to me, is that we are removing the exponential.
mhm.
We are removing the exponential, which also means we are removing trigonometry. So we don't have sine, cosine, you
Yeah,
don't have Gaussians, you don't have the Fourier transform. I think one, you're losing too many tools. And even if you can make some other thing that sort of work kind of in the same way at that point,
yeah,
and uh, um, and the fact that you're losing too many tools like this that are useful in physics, I think it's a smell that tells you, yeah, you're giving up too much.
yeah.
Then there is another thing, which, again, I don't think that physics can remove infinity anyway, because as we're trying to argue, physics, the thing that when we write the laws of physics, we write the laws on ensembles, on infinite collection. We say whenever we have something, whenever we prepare something, we're gonna measure something else and so on. So the statement that we're making are on ensembles, and ensembles are anyway abstractions. Like we never prepare the ensembles, we prepare instances of the ensemble. And the fact that we require reproducibility, you're already saying, I'm going to be able to prepare one more time. Therefore, the ensemble is, at the end of the day, an infinite collection. So at the end of the day, if you buy this argument that at the end of the day, whenever we write a physical theory, we write something that it's about infinite collection, what is the problem of allowing some types of infinity in the math that is still going to be able to, that it needs to talk about the objects that are infinite anyway?
Okay. By the way, do you have maybe another good example for these sequences that reordering matters? Because I just remembered um in quantum mechanics and infinite vector spaces, the basis that we use, the Schauder basis, it's
Yeah.
not even a set, it's a sequence.
Ah, okay.
Um, so I was just curious if that even matters. Like, could I use the same set, reorder it, and then I would get, I don't know, different coefficients or something like that?
So this is something where my problems with Hilbert spaces and Schwartz spaces come in. So if you think about a Schwartz space, right? It's a space where how you go to infinity matters.
How you go to infinity, meaning, I mean,
How
it's not,
fast you go to zero at infinity matters,
okay, for the function, yes.
right? So you imagine that again, you have a function. Let's say that you have a sequence of integers that sums to one.
Yeah,
Okay. And you know that you could have the exponential function is one of these possible ways, right? It's
yeah.
you take one half to the second and so on, and you have something that goes down and it sums to one. Okay. And so now you have a sequence of real numbers that sum to one, and
Mm,
it goes down like an exponential. Okay, it goes faster than any polynomial. Now, suppose that you take that sequence and you stick a zero in between every two elements.
Yep.
So you have one of the elements zero, another of the element is zero, and so on. That thing goes to infinity at the same speed.
Yeah.
Okay. Now you can imagine of padding more zeros every time that you go at infinity, right? And so you can sort of keep pushing values away farther and farther apart as you go to infinity. So that makes the convergence of the sequence slower. And if you put enough zeros such that you blow up the number of zeros exponentially, right? You're gonna get something that doesn't go to zero anymore. Like it doesn't go to zero as an exponential anymore. It's gonna be slower than an exponential because you're padding zeros at a rate that is faster than that it's an exponential.
So if I would draw like a real, like a line through that thing, like I forget the zeros, you mean?
No, no, I mean, so you have let's be a little bit more precise. So you have sum of pi, right? And that goes to one. That sums to
Yeah.
one, right? And if the thing is decaying like an exponential, you can have sum of I to the n times pi, right?
I
And
to the
that,
end, you have some basis.
right? And that's gonna converge.
Yeah.
Okay, that's basically the idea. That's sort of what you when you have a Schwartz function that's what you want. You want that the rate of pi goes down fast enough that whatever polynomial you stick in front of the pi when you're making the sum, when you're making the expectation, you're gonna get something finite.
Yeah.
Okay.
Yeah.
Okay, so now what you can do, now you have one of these sequences, right, as I said, that goes faster than any polynomial so that all your expectation for all your finite x to the n are good. Okay? And now you stick zeros in between,
Hmm.
right? Such that you push further and further. So for every
Ah,
pi, the pi stay the same, right?
yeah.
But the I on which you are calculating the pi is bigger, so that your I to the n is going to be significantly bigger than what you were before.
Okay. And then if you take expectation values, let's say, for this kind of thing, then they can become they will change. I mean, they have to change. You push stuff further out, but they can then diverge. Okay.
Yeah, and then you can make it diverge. Okay, so now let's go back. So now we
Mm.
just did it by padding zeros. But as we in the previous example, we saw that padding zeros could be equivalent of reordering. Because if I start with my probability distribution such that is number zero, number zero, number zero, number zero, then I
Mhm.
can take the things that are farther away, bring them closer to me, right? And
Mhm.
push and use that to push things further out.
Okay.
So I
I
can use the
mean, and then you say you would go from a finite to an infinite expectation value, and
exactly.
this was, I mean, the reordering changed what's observable, whatever.
Right, you,
That's
you
right.
basically are going outside of the Schwartz space. That's kind of what I'm saying. Is
Okay,
the,
and that
the
is, but
Schwartz
this is
space has a notion, has some notion of ordering. I don't know exactly what notion of ordering of the basis has, but it clearly has some notion because if you can make reordering and break the fact that you are in a Schwartz space.
yes. Okay. Basically, I mean, the most naive way would be to just assign any label, like any index of your basis function, just the number, like the index itself.
Yeah.
That would be your observable. So then changing the order changes this observable, and it will, yeah, map a observable with finite expectation values to one with infinite
Right.
expectation values, I guess.
And again, in
Okay, yeah.
quantum mechanics, this is literally what you have when you have the Hermite for polynomials for a harmonic oscillator. Like you know which one is the ground state, you know which
Yeah.
one is the first, and so on. So it's not always just a mathematical convenience and so
Yeah,
on.
sure.
So you have a real ordering of the basis. And again, the Hilbert space instead, because the only thing that you need to require is that the sum of the PI converge, you can do the infinite reordering. Like if I give you a basis, the ordering does not matter. And that's, somehow why some things are nicer to prove because you don't particularly
Okay,
care.
so the state space does not take care of this, or it doesn't even.
That doesn't know,
Yeah, yeah,
right? There's not enough information in the topology, in the structure of the space to know which one you have, and which I think it's a problem. It's not a.
yeah. The convergence of a sequence never depends on the order, right? Because just if you have an accumulation point
Well,
and so on.
at that point you have, it's just the sum of the PIs, right? So it's the sum of your
Yeah,
coefficient,
yeah,
right?
yeah,
And that's stable under any reordering,
yeah,
even infinite reorder.
yeah.
While if you have the requirement of the short space that things converge with your polynomials, finite reorderings are fine, but infinite reordering in general not. And I do not know whether there is a way to characterize which type of reorderings are good and which types of reordering are not. I have no idea.
Okay.
I just know that it's clearly important because I can construct counterexamples that break the space.
So would the goal be to somehow um know something like classes of observables that are consistent with each other or something like this where you okay.
Yeah, yeah. I just don't know what the rules are, but yeah.
Yeah, okay.
So when people do the algebraic approach, right, they assume that there is an algebra of observable and you can do the products. And so I have no idea how to justify that. Like, why is that? I don't even know what the product is because, in quantum mechanics is not like what is the product of observable? So,
And the algebra is even like the like in quantum field theory, it's the not even observables, right? You have the ladder operators, they're not self-adjoint, so there are even crazy operators that are not observables.
yeah.
So and yeah,
So I don't
I
know
don't
how
know exactly what they
that's,
represent. Yeah.
yeah.
Um. Yeah. Oh, there is one other big thing that maybe this is related to your notion of states and processes that I'm not familiar with yet, but I noticed that I think you in quantum information theory they're already like totally used to that that you don't really distinguish that much between a state and a process. You can think of the state as the process that generated it, like the preparation
Yeah, okay.
process kind of. Is that because I always get confused. Like for example, operators, uh, I mean density operators
Mhm.
and observables, and then operators that create states. Everything is just an operator. But they are like, I don't know, they do very different things.
Yes,
Like
yes.
why is there like no mathematical structure that tells me what is what? Like why is it just a physicist in his brain, like keeping track of what it means?
No, I think there should be. It's
Okay.
so the problem is a little bit similar to what you have in classical mechanics.
Yeah.
If you're thinking about the states as probability distributions, well, those are function of position and momentum.
Yeah.
And if you're thinking of observables, well, those are function of position and momentum,
Yeah.
right?
And
And
each of them also generates, I guess, some
yeah,
kind of
you,
translation,
you can you can
whatever.
imagine, and those can generate some type of transformation as well.
Yeah.
right?
Okay.
So it's
That's
not
common.
a feature of quantum mechanics. Let's put it like that. So I think
Yeah,
it's
that's good.
useful to recognize that it's not a problem of quantum mechanics. It's a problem of the representation.
Mm-hmm.
And I do think that so what happens is that at an abstract level, you are going to have two spaces. One is the space of ensembles,
Mm-hmm.
and the other one is the space of linear operations or linear maps from those ensembles to a real number.
Yeah.
Okay. And those are the those are the statistical quantities that you
Yeah.
call observable in quantum mechanics. Okay. And again, not necessarily all quantities should be linear. The entropy is a quantity that you assign to observables, and it's absolutely nonlinear. So the fact that we, only look at linear quantities, okay, we're already making some. But anyway, let's make those.
Yeah.
And so now you have a linear space that acts on another linear space, essentially.
Mm-hmm.
Right? And a lot of the math that we use in physics, which can be, yeah, there is the whole topic of topological vector space and function spaces as seen from the dual of the topological vector space that you act on. This sort of makes sense physically if you start thinking like that. Now, the issue is that in both classical and quantum mechanics, these ensemble spaces become essentially operations or measures on some space of points.
Mm-hmm.
And in classical mechanics, it becomes the probability distribution of X and P, and in quantum mechanics become the density matrix, right? And then the observable becomes the integral or some type of sum of the product of the actual ensemble times some other operator on that ensemble.
Yeah.
But it's that ensemble represented in this space of points, whatever we are going to call it, because in quantum mechanics, they're not really points. They're going to be a basis, which is not really a basis because on the continuum, it's on a spectra.
Yeah.
It's the spectra of some, you pick some complete set of variables, and then you generate the spectra, which is all the possible values of those, and then you have something that lives on that space.
Yeah.
And but that's the representation. So the object looks the same because you found a convenient representation and so on. So the thing that should
Yeah.
happen should be that for every ensemble, there should be a corresponding special observable
Mm-hmm.
that has some kind of nice property, which I still don't know what it is, that such that when you represent them in this space, they actually become the same mathematical object. So
Yeah.
the fact that you have a probability distribution on position and momentum, and the fact that you can have a function that is actually the same that has the same value on that probability
Mm-hmm.
distribution, those two things should be two different physical objects, and so even mathematically they should be slightly different, but they just happen to have the same values. And if I were able to know what is the property that those observable have on that particular state and only that particular state,
Mm-hmm.
that would be a tremendous help. But I still don't know what it is.
Yeah.
Again, maybe somebody knows. Maybe if I were able to formulate the question in the right mathematical language, I would be able to find it. But then it's one of those things that knowing the mathematical language on which to formulate it would be that I already solved the problem anyway. So.
I see. Okay, I think I got a bit sidetracked, but and now it would be really great if we for the whole computability business,
Mhm.
if we could somehow agree on an approach. I think Mark would have to say about it?
Yeah, I know why well, maybe he was busy and couldn't join, but whatever. Maybe we'll
He's
have,
busy.
maybe, I don't know. He's not here, so I don't know
Okay.
where.
Anyway,
Mm,
you probably I will put it in Discord. So, just a summary, and then what I still
yeah,
want to know, and then maybe we can somehow settle what is an interesting direction.
yeah. So to me, as I said, like it needs to be clear what is the problem that we're trying to describe, and then depending on the problem, you are going to how can I say? Uh, you're going to have different things that you care about. So
Okay.
the thing that I don't like a lot of the time, how the debate is posed even within math, it's like there is one right way, right? So a lot of the time, people who do the standard math things, those are crazy people. We don't care about them. And the people who do like again those more constructive approach think, oh, the other thing is nonsense and whatever, whatever. And I don't think it's useful. I think that you're generally looking at two different problems. Like one is what can I prove, and the other one, what can I prove on things that I can actually compute and manipulate. And another interesting part that ties to this thing, I had a nice, I found a nice paper at some point, and I started chatting with those people, but then I guess they didn't have time with the conversation physio. Maybe I could have them come and present here. But anyway, they were making this wonderful point. They had this paper is essentially on, well, they also, some of these people that think about the universe as a computer and what can be computer and all of that, right? But one of the arguments that they will make very clearly is that if the universe is a computer or computation device or whatever you want to call it, it doesn't have to be a Turing machine.
So, isn't if the universe like nature?
Yeah. So the point is that there are different, you can define different models of computation. And you can even define models of computation that allows for some classes, and there are different classes of infinite computation.
Is it like so? As far as I know, all the ones that were defined were found to be then equivalent, and then you can define something like you have an oracle that just gives you the answer for free, and then you can consider machines that can use this magic oracle
Yeah.
to build stronger machines, but you can then even build even stronger machines and so on and so forth. But um, I don't know, those are like abstract, just
So even in those cases, the standard literature always consider the machine a church Turing machine. So something that
yeah.
has a finite memory, has a finite set of instructions. The inputs and the outputs can be infinite, but and the time that it can take, it can go to infinity. But the numbers of instructions, the memory that it's allowed, it's always
Mhm.
infinite and finite discrete pieces.
Yeah.
The argument that these people are making is that, well, that's one model of computation. Like you could
Yeah.
have other models of computation. You could allow that the program could be, indefinitely longer, that the memory that you have access to is infinite or countably infinite or even more infinite. So basically there are people that study, at least from what I understood by reading what they were writing, that there are different classes of computation that you can build. And of course, if you have a class that it's bigger than the one from the church Turing, then you could use that class as an oracle to the Turing machine.
Yeah, by
Right.
the way,
What?
I think Mark just got screwed over because daylight saving time started already in the US, but not in Germany.
Ah,
It's again this year it's 3 weeks. Last year it was
yeah.
the same just for one week. It's funny.
Oh no. Okay. That's what okay, that's what happened. Okay. Well, I don't know if you want to give a summary and see if you can jump
Oh
over.
no, wait, it's even
But
wait. Even on
I thought that Discord would take care of all these things.
no, he's right. On Discord it says starts now at 12. That's funny.
You're right. But what happened on YouTube? What was the notification on
He
YouTube?
was fine. I don't know if you defined the time on Discord in a different time zone. I don't know.
Because so on YouTube, let me see what happened on
I
YouTube.
mean, on YouTube we're
Oh,
live.
YouTube is started at 11 a.m. Yeah. Yeah, because I get a notification every time that I get.
Yeah.
Okay, well, that was the mystery.
Yeah, maybe the Discord server or something is some
Eh, I don't know. I'll look at it offline and but yeah, starting in 2 minutes. Yeah, yeah. Definitely the Discord thinks that
yeah,
that's it. Okay. Oh man, well, whatever. It's always funny because in the fall they're synchronized. So
yeah,
yeah, I don't know. Anyway, let's have him join. So. Time mark. I didn't. I didn't think about
Yeah, no,
the time
that's
zone.
a common issue.
Yeah. So, well, I can tell you what we chatted about. So we did chat about for the sort of computability and some of the issues.
Mhm.
And one other thing that my perspective that sort of the way that I've been looking at things. So now you can tell me whether you agree or not. Is that sort of that there are two classes, let's say, of mathematicians. The one that care more about what can be proven from a set of starting points, and this is, let's say, the standard way of doing mathematics. And then you're gonna accept axiom of choice and stuff like that because they're useful tool to prove things. And then on the constructivist side, then what you're really trying to do is you really want to limit yourself on objects that can be constructed in the sense that they can be thoroughly specified in everything that you're doing. And sort of that's where you are going, to limit yourself and not want things inside your proof that allow you to create things that go outside of that realm of study. That's basically it. And then
Well,
go ahead.
I'd say that was correct, except for the first statement. You said that both of them limit themselves to certain like axioms. It's just uh, different or on the constructive side, fewer fewer standard axioms, and then they can have more like wilder, more exotic ones instead to get to where they want to go. Um, Depends on like the many approaches then, right? But axioms are gonna play a role either way.
Yeah. And I'm not saying that. It's just that the axioms that you have are more restrictive because you want to narrow down what are the things that you're talking about. So things that are things that you can actually construct, they have to be, for example, representable infinitely many symbols. So something, I gave the example of the well ordering of the real. That's something that you can say, oh, it exists, but you can't write it
Mhm.
down with finitely many symbols. So you don't want it constructive mathematics and stuff like that.
Yeah.
Yeah. And then what I was arguing is that in physics, we care about something that it's, I guess, falls a little bit in between, because what we're interested in are things that we can experimentally define, experimentally verify.
Mhm.
And whether something is, for example, computable, as long as we can narrow down the function well enough, whether it is computable or not, since its nature that it's doing the computation becomes less important, let's say.
Mm. Yeah, it's like the computability of stuff that literally talks about being able to do it at all, right? So any realization of a computer has to be built on physics in the end. So if it's not computable, then you can literally not build a physical experiment that will tell you the answer.
Yeah, but it's the physics that decides what is computable. So if
Sure.
a
Yeah.
relationship exists, then by definition is computable. So
Mhm.
what I need to check is whether I can experimentally define something that I can recognize that something is doing that particular computation. So suppose that I have again a map from okay. So first of all, real numbers, right? So,
Mhm.
okay, we can't represent the real numbers, right? But I can still imagine that there is a physical quantity that every time that I go to a higher level of precision, I get some better and better value approximation for that,
Yeah.
right?
I think in practice you end up with basically decidable reals, right? You cannot get more reals than the decidable ones with physical experiments, I'm pretty sure. Because in order to decide, you have to be able to measure the difference. And if you can't do that, then it's no longer decidable. So it's kind of
Here's the problem. The other problem is that at the end of the day, the reals are there as an abstraction, an idealization of what we can actually do, because we can't really make things that are, that at some point we're not going to have the infinite precision. So the reals
yeah.
are a model of what we have. And we can, inside the model, always get something that is better and better specified, right?
Yes.
And as long as you assume that you have the limits, I don't see why, like, how can you tell which are the reals that you're going to be able to find and which one that aren't?
Um, I know the thing is that I don't really know all the details there, but you can actually construct the decidable reals, like
Right.
all
So,
of them. Whereas the
mhm.
non-decidable ones, you don't necessarily can construct all of them.
So the way that I see this in terms of the way that we construct the real in the project is the following. So you take, you assume that you have references. And a reference is something that allows you to say the value that I have is above the reference or below the reference.
Mm-hmm. Yeah,
So,
that's like an interval of where the value must be. Yes.
right. And this is going to be, the topology is going to generate by statements like this. And then you have some conditions of essentially that allows you to reconstruct the fact that that these references are ordered. And then once you know that you have a countable basis, because we need to be able to explore the whole space with countably many verifiable statements.
Mm-hmm.
And so the topology is going to be countably generated.
Yeah.
And now the idea is that if I get a sequence of my references,
Mm-hmm.
even if it doesn't, let's say, converge to these original countable references, since I must be able to get the countable union of that references, so I'm going to be able to say, oh, it's greater than reference one, it's greater than reference two, it's greater than reference three, and so on, right? And now you can imagine these essentially these countably dense references. You can make an isomorphism to the rational numbers.
Yeah.
And then you are basically taking the union of sets that are x or greater over the rational numbers. And once you make the unit, you're going to get the limit. And therefore, you're going to get all the set of numbers that are greater than the limit, the intervals that are from the limit to infinity. And so you get essentially by choosing any of these sequences, you can get to any limit of the rational. And so every limit of the rational should cover all the reals.
Yeah, I mean, the way you implement countable reals as far, or like decidable reals, as far as I know, is basically via interval arithmetic, where you have, okay, it's between those two rational numbers, and then you just refine that interval as far as you like, but you can never go to a refinement of zeroth. Basically, it's just arbitrarily small, but not completely zero, because you can't even decide whether something is zero necessarily, right? Like
Yeah,
that's one of the constructive things.
So I know that a lot of things that it's done in at least in computer science, they typically work with let's say things that are always partially defined, and then you basically consider the collection of all the things that are partially defined. So for something like that, you would basically say, well, I never have the full string of infinite precision, but I have all the finite precision ones.
Yeah, absolutely.
And then you work with that.
Yeah.
And if that's what it means by the constructible reals, that I understand what it is, because I've already seen it.
Yeah, I'm pretty sure that's that. I think so. But like, you shouldn't necessarily take my word for it, because it's just from broad reading. I didn't really study it in depth.
Okay, sure. I mean, can I maybe ask again? So I know even less than you guys, so I just
interrupt us.
So I guess decidable in this sense means hypothetically, I measure the position of a particle on a real line. And then you're saying I'm already given all the data, meaning for like I have if it's decidable, there should be a sequence of intervals where I measured whether it's inside or not. And then I have a computer program that could, like, for this sequence, step by step tell me which real number it is. It would take like infinite time, but there's a countable sequence of computations using some countable number of intervals that I measured that would decide which real it is. Is it something like this? And there are reals where I don't have that?
Yeah, I think so. Like, so there's the concept of a Zeno machine, which is like an extension of a Turing machine where you allow infinite time computations. And I think with that you could get to sort of infinite precision, but you still wouldn't get all of the real numbers, because some of them are just not decidable. Like, their existence depends on solving the halting problem, which you can't do.
Yeah.
Right?
Okay.
So like, it's not that they don't exist, but they're literally unreachable. You cannot prove that they exist, and also not prove that they don't exist.
Yeah. That just means it's kind of metaphysics.
Yeah.
Whether they exist or not.
But also in practice, I think that means that no experiment ever would yield one of those, because if it did, then you already solved the halting problem, right? So I don't think, like, those are the decidable ones are the ones that are physically relevant, I'm pretty sure. Like, you can't possibly need more than those for physics.
Okay, so I think I might see the issue with the argument that I was saying before, because if I want to say that I want to create a limit procedure, right, that says, okay, I want to measure, I want to measure pi, right? And so I can only measure if something is greater than a irrational number, but I want to measure whether it's greater than pi or not. I have to make a limited precision because I basically have to say, well, first I check this reference, and then I check this reference, and I check this reference, and on. So I need to have something that tells me what is the sequence of references that I have to check for, right?
Yeah, I mean, that's a choice of you, right? Like you choose your experiment however you like.
Right. And I think the fact of whether one particular real number is something that I can check depends on having that sequence of real numbers that then I'm gonna approximate to the real number.
Mm-hmm. Like you cannot use
Yeah, like Tobias thing so that he can catch up,
yeah, you cannot use like a reference that you haven't already built or constructed, I guess.
No, even suppose that I have all the rationals, right? So I know how to construct all of them, and I have a
Yeah, that's
way
easy enough.
to iterate over all rationals. So I have all the reference for the rational, and I know how to iterate over all of them, right? If I want to create a sequence of rational, I have to have another iterative process that spits out what is the correct sequence of those references. Okay, so this is actually clarifying for me. It's exactly so. One of the things that we were talking about before, Mark, is the fact that what's his name? It's basically the question of whether the fact that I had an iterative process for the basis of the topology was enough for doing all the construction that we are doing. And I think what we are saying here is that it's not. Because even though I have a way to iterate on the basis of a topology, the fact that I can construct every limit point, it's a different set of iterable structure. And in fact, I will need an iterable structure, one for every point. So, but that also becomes a question, an interesting question. Then it is not true that I will be able to take the union of any collection of verifiable statements. Like in principle, so if I say I can take the union of any verifiable statement, I need something that allows me to iterate over those statements.
You need like an order? You need an order in which you do that? You need to write a protocol?
Yeah, exactly.
For an experimenter,
yeah.
do this in this order? Yeah.
Yeah.
So, okay, well, if you just stick to finitely many intersections or unions or whatever, I think that's the same like finite sums on products, where it's always the order doesn't matter. It's only once you get an infinite case, it starts being fishy, right?
Yeah. Okay. So right now, I can confidently say that right now that the axioms that we have are not constructive, because we are saying that we can always take the infinite union of verifiable states.
So I know that the formal topology, what that I've been talking about, is technically both constructive and predicative, which is also good. So you can't have stuff that you don't already have, basically. And that one has infinite unions, I think. It just has finite intersections, but unions are arbitrary.
Yeah, but
So I
but
think
again,
that actually suffices.
I think I need to define what. So if you're saying that all the infinite units are fine, then you're saying that I can get all the reals. Because all the reals I can see, the references for the real can be seen as infinite union on the reference on the open sets of the rationals. Like, all the open intervals between real numbers I can define with open with infinite unions of
I
open
mean,
intervals on
you,
rationals.
you get the entire space, but you can't hone in on all of them because for honing in, you need the intersections.
I understand that I cannot hone in, but the way I don't care about the honing in. What I care about is being able to recover the reals from all the
I think that can be like just the space as such, the topology of the reals can be constructed, I think, with opens. That's what I've been trying to read on lately, and that's the I guess the feeling I got from what I read. It's basically something I just started reading, so it's not like I know this
yeah.
by heart, but I think the topology of the reals can be constructed just fine. It's just the honing in that's like the
Yeah.
decidable reals. That's about which ones you can actually hone in on, not about the topology as such.
And but you so we do pointless tautology. So we don't start with the points. I start with things that then become open sets of the points that are defined essentially by the intervals. So
Yeah,
if I can define the points from the intervals, right? For my from my pointless topology, that's all I care.
yeah. I think from that perspective, you're already constructive. That's fine.
Yeah,
Or
but
I think
I still think that if I want to be technically precise, right? If I have a set of an infinite collection of verifiable statements, but you're not giving me a way to iterate over those statements, then I
so
can't create the conjunction.
that's the predicativity portion, I think. Like the predicativity does not allow you to just arbitrarily iterate over infinite stuff. Like you can't iterate over all sets, for instance. You have to actually construct the sets first. But it still has a notion of that anyway. You just have to be careful to be predicative about it. But that's very technical stuff though, where it's like I'd have to really
Okay,
read
it's beyond
to
your level of understanding. That's fine.
yeah, but I
It's
know
beyond
for a fact
mine as
that
well.
can be solved. So um, it's been solved already. That should work. Like
Okay. Do you know
predicativity.
somebody who we can invite here to chat about these things?
No, I mean I can tell you the authors of papers or whatever, but no, I don't personally know.
Yeah, no, I meant that. Like, if there is, if you know whether there is somebody in their community that is approachable or that's
Yeah, not particularly. I've just been basically Googling papers and
okay.
looking into it a bit, and not really. Like I can look up the authors and see maybe some of them will, but I don't already know that somebody would be willing.
Okay. Yeah, because it would be a lot easier and productive to actually talk to
Yeah,
somebody
for sure.
this stuff.
I mean, the way to solve it, I think, has to do with so that comes down to type theory, where you basically construct everything as a function, and then you have type universes, which basically allow you to. That's kind of the distinction of where you have what's it called, proper classes instead of sets. The classes are basically in a universe above sets. Because you can have the proper class of all sets, right? You just can't have the set of all sets.
Yeah.
And somehow they use that kind of type hierarchy, like universe hierarchy, like they don't stop at one universe, but they have universes within universes. And it's like universes of statements about stuff, not like physical universes, right? And they can basically always construct the one above from stuff from below or something. And then that way they can sort of fix it.
Yeah,
But
okay. It might become too technical, and then I will say
yeah, it's very
at that
technical.
point, it's out of the type of thing that we're gonna think anyway. So if I can still think about procedures and how do I
Yeah.
define the procedure, it's something that I can relate to what we're doing. If it becomes too abstract, then it's
Yeah, it's a issue, I guess. I know the minimalist foundations might work too because they actually limit yourself. They're really minimalist. They try to be compatible with all the things. They try to be like whether you're constructive, predicative, or classical, it should support all of them. So it's basically the minimum set of axioms you can use that still works in all the directions. If you can prove stuff in that, then it works everywhere.
So what's the difference between constructive and predicative?
So constructive is basically just the don't use the law of exclude middle. You can't decide an or statement without giving proof for which of the two. Sorry, no or is right. Which of the two predicates basically is the right one, right? So you can't say, okay, one of them has to be true, so I can proceed as if one of them is true. You have to actually say, this one is the true one, and then proceed with that one. Sort of, that's what constructivism limits you to. And predicativism is a bit more complicated, but so that basically tries to avoid sort of circular logic of sorts, of the like making statements about huge collections of stuff without having already constructed that stuff. Like you can make statements, but only if you already can show how to construct all the pieces. If you first need to define the infinite thing to then say something about the finite thing, then it's not good, if that makes sense. But it's a bit, it's a very different notion because you can in fact be predicative without being constructive. So they are orthogonal in that sense.
Okay, they're independent choices.
Yeah. Can I? It's best to just read it real quick, but can I find it? That's okay. But, I'm trying to search something. I can keep talking for a bit, but I'm trying to.
I'm trying to think. I don't know if Tobias has other.
But it's basically what limits you to. It's something about resources somehow. Like if you can't already build a thing, then you shouldn't be allowed to use it, right? And that's also speaks to physics for me. You can't just use I don't know, a machine that you can't even build because it takes infinite resources to build.
Yeah, that's true, but there is a lot of things that I struggle because it's like you have a set of definitions that go together, and there isn't really a sense that you build one. So, even the idea that I have processes and that I have states. Well, it's like I use processes to generate state, but then states are the things upon which I define processes. There isn't really one that comes before the other. Like they come as a set together with nice properties.
Yeah, that's fine though, I think. Like there's specific ways where that's still fine. It's not.
But again, the question of whether or how these things are in the end represented mathematically. So I could even use the sort of classical mathematics with all the tricks and bells and whistles, and then limit the thing that I can do on the subject that I like on the definition of the object that I am talking about, right? So I don't even know whether it's important that, as I said, we have the idea that things have to be physically well defined, and we do it through topological things and so on. At the end of the day, I'm going to have a topology that describes which are my verifiable statements and which aren't, right? Regardless of how I'll decide to do it at a low-level mathematical thing, I will have a topological space with some points and some just T0 second countable topology. So I could do it such that the mathematical objects are actual constructive, whatever, or I can just do it with classical mathematics and do it inside that, right? So it's a little bit like saying, I have to write my computer program that does some things, and whether I implement it in assembly, Python, or Java, whatever, it's less important to me as long as the program is doing the thing.
Well, the thing is, if you write a computer program, you're already being constructive, because computers can only do constructive stuff, in a sense. But
the point is that I can go and do a functional program in a functional language, or a declarative program in a declarative language, or I can take a functional program, programming language, and then use it to do other things as well. Like everything is complete. I can do the same thing that I want. So I could use. For my mathematical structure, I could use set theory as my foundation, or category theory. Doesn't matter as long as I have what I care is that the mathematical structure that I have are describing the correct physical thing. So
I think a predicativity in terms of computation is like, if you define a function, then you can call it. But if you try to call a function that's not yet defined, then you're in trouble. And that's sort of what it tries to avoid.
But what would be an example in which I would do that?
Well, for instance, if you try to iterate over all sets, then you have basically to look at all sets, each set individually, and you can't do that if you don't already have a construction of all sets.
Right.
That's the issue, I suppose.
Okay. But can I still define, how can I say, interfaces in computer language?
There are proofs for various stuff. Like I don't know all the details, of course, but there are definitely proofs where you can basically say, okay, if I can prove it in this sort of language with like a classical framework, and then it's valid in all of these. Stuff like that. And that's often done, in fact, like in what's it called? I think synthetic analysis or something. You basically prove that whatever you do there, which is completely constructive, you can in fact find a version of that will work in classical mathematics, even though you sometimes not use the axiom of choice, but actively reject it. Like you say, no, this axiom is completely wrong. And still you can translate it over to a classical way it does hold. So stuff like that, interfaces between different methods do exist to some extent, but I don't think they exist for everything. Just for there's basically you gotta prove that that works. But they're pretty general ones that actually work for a broad range of stuff. And in synthetic analysis, that's useful because you basically have the let's say physicist's trick of thinking of infinitesimals as like fractions and stuff. Even though you're not allowed to do that. If you set it up right, then you are allowed to do that after all, and you can prove that everything still works. Like the issues get exposed in a different way. Like you can still not assume that they are zero, but you cannot prove that they are different from 0 and stuff like that. Like it's just a different way to do it, but actually it makes some proofs easier because you don't have to take the complicated limits. You just calculate with them the infinitesimals like their normal numbers, and it works, stuff like that. So in that sense, because there is a theorem where you can go from one to the other just fine. It's more like a matter of which one is the best tool for the job, like using a functional or an object-oriented language or something.
Right.
But can I ask, predicative, would it be fair to say it's somewhat like in a programming language where you can usually declare a function before you can, and then define it afterwards? So you can have two functions that both call each other.
Right, that is still allowed. Yeah,
it is still
you
allowed.
can have mutually recursive things and stuff. That's allowed. Yeah, it's just it's a really subtle thing, but specific things are not allowed.
Okay.
You can't have completely arbitrary what's it called? Come on, induction. There's certain induction rules that are not allowed.
It's basically when you're trying to unroll the infinite nested calls. Is that when you bump into the problem?
Sort of, yeah, basically. Like, if it... Jeez, this is stuff like, it is really technical, and I'm not
Yeah, it
ultra
might be
familiar
that if
with
it's
it,
too technical,
but it's
it's
sort
not
of...
going to be so relevant for us anyway.
Well, I think it will actually be relevant in the long run, but actually drilling down on the details is difficult. Like, I have to, I guess, read more on it to actually be properly in the saddle with it, and then I'd have an easier time expressing what's going on. But yeah, it's definitely something about you can't have completely arbitrary induction, and certain things are impossible because you'd first use it before defining it. Like, you can define stuff mutually or at the same time, basically, that works. But certain things you cannot even do if you're allowed to do that. And
Okay, so
you need more.
you basically can't have a dependency on the definition that goes one way or the other. It's a little bit like when you have constructors. Constructors in object-oriented programming, you can't have the constructor of the base class depends on the constructor of the superclass, for example.
Something like that, yeah, because that would be imprecate. If you have the base class must be defined first, and the superclass takes from the base class. It can't go the other way.
Yeah.
Because that would be impredicative.
Okay.
I think that's basically the gist. And I think that's also relevant in physics for setting up experiments, because you can't rely on a detector that you don't even have yet, sort of.
Yeah, but as I was saying before, like the way that I see things working in the definition that we're gonna do, it's like I'm gonna give you a set of consistent assumption of the object, the thing that you can measure on, and so on, right? So they're all given at once because they have to be given at once.
Yeah, I think that part is fine still.
Yeah.
Like, you can't just say, yeah, that basically in this type of mathematics, everything is in terms of functions. If you can give a function that's like decidable, then I think you're fine. But it's a very specific style. Yeah.
Do you think the paper that you shared about, what was it, pointless topology?
Yeah, I shared two
Topology
papers,
in
right?
the topology in the minimalist foundation must be point free. That's what I'm seeing.
Yeah, that's the later one, and I also shared formal topology and univalence or something.
If
Do
we're
you think
talking
they're
about
good
specific
introductions to
papers,
what they're doing?
I probably not. one of them is more like the second, I guess the one you mentioned first is more of a philosophical paper. It doesn't go as like it literally talks about the reasons why from a philosophical point of view. Whereas the other one is really technical, and you kind of already have to be familiar with like homotopy type theory and stuff, and that's like it's doable. It's not impossibly hard, but it's still a new language you'd have to learn, and that's obviously quite a lot of effort and not really what you can be expected to have from a introductory paper.
Sure. Yeah, so also my original confusion, let's say, was that I totally see in all of this how this kind of resembles the like restrictions that you find in a lab, like only stuff you can actually build, and you have finite time, finite resources, and so on and so forth. I totally see the connection. What I was confused about is somewhat maybe at what level this is built in and stuff like this, because I mean, in a sense, we are not doing physics, like what we actually do ourselves. Like we don't even do science, right? I don't use a scientific method. I just I construct stuff, right? I talk about the scientific method. We are, of course, on a meta, right? So that's why I have other tools and I have other restrictions in what I am doing, and I want to prove stuff. So what if I just use the axiom of choice to prove things about things that are constructible? That could be totally fine.
Well,
that's the thing. Like, unless I, of course, constructed things that don't even exist or like that have no physical relevance.
That's process. Yeah, that's sort of the thing with
of course,
those
I'm
axioms.
just doing something wrong, right?
Yeah, well, it's not like you can use it. That goes back to what I said earlier about there are proofs about being interoperable. Basically, you can just translate one to the other, right? Sometimes you can't though, and if you use the axiom without thinking about it carefully, then you basically can't know whether you're in one of those situations. That's the issue. But if you're careful about it, then absolutely you can.
Yeah, that's what I was guessing, but maybe this then just comes down to like experience in practice. Like, is it easier for me? Like, for example, I said I was just curious about computability and found a book which in the introduction said they use classical mathematics and then they define what they mean by computable. Everything in terms of, the usual mathematics, and then they just show what kind of stuff in physics is computable, like eigenvalues of self-adjoint operators and stuff like this. So they don't, and then in the preface they talked a lot about the fact that they use this approach and they don't use any like constructive axioms or stuff like this. Apparently, because this would be like the more natural approach to the people in mathematics that would read this book. So that's just why I was curious. So apparently there are two ways. And somewhat I have a free choice of how to do this, and it's a matter of what's more convenient. And that's why I was trying to clarify or hoping to clarify what's
sort
necessary, where can I just make a choice, what's more convenient, and maybe it's more convenient not to go all the way down to the accents. Like
just to interject, Tobias, this is basically the approach that we have taken for the book in the Assumptions of Physics. Like we tighten out the definition of what we're talking about so that it's clear that those definition have a specific map to the physical ideas of verifiability and so on. But then we just study study those properties with standard mathematics.
Yeah.
Yeah. It's really a matter of being sure that it's allowed, and basically what not taking an axiom means is that you have way more possibilities automatically, because every proof that relies on the law of excluded middle basically collapses all the situations where you don't have a true or no false, like all the undecidable ones, for instance. They still have to be decidable according to that axiom. And I think there is a lot of this is pretty cutting edge, I guess, in the sense that it's really being researched by mathematicians right now. So in some instances, it's also just a matter of the tools not quite being there yet. They are being worked on, the tools themselves. But a lot of structure is being missed by using those axioms, which can be fine if you're not interested in that structure. But if you want realizability, for instance, then that kind of structure might actually matter to you, right? But of course, if you know it won't be a problem and you could just construct the equivalent in the other theory anyway, then you might as well use it if it's easier that way.
Yeah, so there are a couple of things that sort of make me wonder whether it's useful or not. So, for example, one of the things that we assume already when we say, the principle of scientific objectivity, we have statements that are objective and therefore they must be already true or false for everybody. So I think there is already there an implicit assumption of this
Decidability.
right?
Yeah.
And it's not that, but then you say, okay, now I have ways that I can access the truth. I have the verifiable statements, and there you have a three-value logic because, yeah, the statement might be true, but you can't determine experimentally. So, there may be a fact of the matter that the mass of the electron is a rational number. Sorry, the ratio between the mass of the electron and the mass of the proton is a rational number, right? There might be a truth to that, but it's not accessible experimentally.
Yeah, I mean, you also give the example of the seventh quark or something. You cannot ever know
Right.
that there are more than 6 quarks.
Right.
That's
And so the cases in principle in our head exist, and I think it's still useful, when we're doing physics, to think that those are actual cases that can be true or false, or that can exist or not exist. And I do not know what would be a physics where we have statements where it's not that the truth is not accessible, but the truth doesn't. I guess if the truth that doesn't really exist, I think you botched the model like beforehand. Like you just have to change the model and find some other model.
Yeah, hold on. There's I actually sent a Quanta magazine article about this sort of. What was it? Because that just happened to be coming out right when Tobias asked about it.
Yeah, you sent it to me.
Yeah, I'll send it in the chat now. There you go. Whatever.
That's what also reminded me of what Gabriele was talking about. It was they mentioned also an example from condensed matter or something where you would have undecidable things that you cannot compute.
You can't compute whether the property is there or not.
Yeah.
And in this case, they literally do it with basically classical physics, and they can construct stuff where you cannot decide the outcome over infinite time. Eventually hit a limit, basically. And that's just basically, okay, you can have a arbitrary Turing machine with classical physics. I mean, that makes sense because we have computers. Never mind that they rely on quantum mechanics in part, but still. And then, of course, you can get situations where you cannot get an outcome because that theorem already tells you that it won't be possible.
Right. But again, the nature still has the property or not the property, right? So the fact that you
it's just not provable.
Yeah.
But you can also never confirm which one it is. So it's still it's a pretty subtle problem. It might well be true, or it might well not be true. You just cannot ever know.
Yeah, that's also maybe Mark, something about this. What if I had the other case where I cannot predict what it is, but I might have defined beforehand what the correct solution is. I cannot just can just
I
that I
mean,
can predict it, and then I find out what it is, and I might be able to check that this is the
or
correct
there's
option.
stuff like that, like functions where you have you, you cannot possibly invert it, but if you have a solution, you can check it easily.
Yeah, right.
That stuff, like that's how cryptography works, right? That depends on functions like that, where you basically scramble information, and it's easy to check that you got the right value. That I guess you have a login, but you cannot easily unscramble it.
Yeah, that would still be fine, right? For us.
Yeah.
This
I
is
mean, I said if it runs on a computer, and cryptography certainly does run on a computer, then you're
yeah.
definitely fine, because then you already have a thing that constructed the thing.
Okay.
Like in the computer, in the end, also depends on physics. If it's
Of course. Yeah, it's just that in the example, of course, the Turing machine is not finite. So
but in this case, it's even finite because you have finite
yes,
time cryptography, right? Because otherwise, we couldn't have this chat right now because it's still trying to decrypt the connection or whatever.
but it's just very hard to invert it, but in principle possible, even in finite time.
Yeah. I mean,
So
usually it's like exponential or something like that. Like
yeah. Okay.
it takes
But
millions of lifetimes of the universe to get to the solution or something, and effectively it's impossible, even though in principle eventually it would be.
okay, but restricting ourselves to just computable things is too much, right?
Is it?
I mean, in the sense, like it's computable. Given an answer, it's computable whether it's the correct answer. But stating beforehand that I can only make statements like the hypothesis of this outcome being true, that was not computable. Like I cannot predict actually. I can define it beforehand. That would be like a non-computable function. Given some, I don't know, some input, I predict what the output is. Or I
So
define
have
what
an
the output
oracle
is,
process.
but I cannot. Sounds like it, but like it might happen that I cannot compute it, but I defined it beforehand. Then I found the outcome, and then I check, yes, this is actually what I defined beforehand. Isn't that
I mean
fine?
that's a completely different problem, isn't it? Like if you already put in the solution at the start, then you already have the solution. Then there is nothing to compute per se.
I somehow define it, like I don't know.
Yeah, sure. But that's putting in the solution at the start if you define it that way. Is it not?
So it's just, but it's not computable. Like I say, I don't know, this is the solution to this equation, but I cannot compute the result, like even in principle, I cannot. But if you give me the solution, I can check, I can compute whether it has been the right one. So there was like no computable function that could create the prediction, but there is one that can check it.
So,
Yeah, so there's the
so
two
what?
different classes of
Yeah,
problems.
it goes in like two ways, right? It's like so, but then
Um,
if I restrict myself from the start to only statements that where I can compute beforehand the exact
I guess
outcome, that would be too
that's
much, I guess.
yeah.
That's what I'm wondering about.
It's what you're saying. I think is a really strong requirement. Like that, like not being able to compute it includes like via just brute forcing it, basically giving you every single possible value, and then trying to get it. Effectively, the only way to get there would be sort of like finding an undecidable real, defining it as an undecidable real. Then you cannot possibly compute it because it's one that requires the halting problem. But otherwise, like
Yeah, you're saying like the counterexample that I suspect, like where I just mentioned could exist. You're saying it's like very unlikely that something like this exists, where you cannot calculate it beforehand, for a finite system and whatever. But there might be that in this example you can still verify afterwards that you had the correct prediction defined beforehand. I'm just saying it's very unlikely that we get something like this. Or are you saying I don't know?
I'm saying that I don't think it would ever matter
Okay.
because
So in our case, going back to the physics, right? So if you have a
Yeah.
prediction, like you should be able to go and verify whether the outcome matches the prediction, right? So
Mhm.
at any rate, if you have something that you can't check experimentally whether whatever prediction you have is true or false, or you know, we can verify your prediction, that is not physics. So at the very least,
Yeah.
you have to have that the function is continuous in the topology where the topology represents what you can actually verify, right? So that's the bare minimum, and that's what the experimental verifiability is going to be able to guarantee. Whatever is your topological space of your initial premises, which you also need to be able to verify, because otherwise you can't check that your prediction is needs to be valid. And whatever is the topological space of the outcomes, right? There is going to be some topologically continuous function between the two. So that's the things that we can always guarantee, and we cannot guarantee. At least I don't see any reason to say that that function, that map from the initial space to the final space has to be computable in some externally defined computable system and so on, right? So for that to be defined to be computable, you need to define an encoding of the initial condition on some space of inputs to your computation, and a function that does the computation, and a non-marshalling of the output of the computation to the space of verifiable statements on the outcome, right? So whether that whole process exists or not, I don't see it as a requirement for the fact that I will have a set of inputs, a set of outputs for a physical processes, and I can check it.
Well, a function is a very general thing. Any like machine you use to measure a thing would already be like a black box function. You put something through the machine and it gives you a readout, and that's the function. So
Right. So the point is that you always can natively use the process to verify whether your prediction is right or wrong. But that's the actual doing the experiment. So this would be like saying, oh, well, we don't need to write a quantum field theory and have a supercomputer that do calculation on quantum field
Sure.
theory, because we just make the experiment every time that we need it, right?
Yeah,
So
and in fact, that's an approach that's used, I think, in quantum mechanics. Like they basically set up a not Turing complete computer of sorts that solves that one problem, right? Each quantum experiment is like a limited computer that solves that one problem.
right, you can always do that. And in fact, if you can have a unitary transformation that solves matches the process that you have with your process in which you're doing the computation, that's going to be something that you can do, right? But again, the fact that what I think people think about computability in these matters, I think they always mean that you're doing that process on a general Turing machine and do the computation in terms of some generic and a particular representation. Because otherwise, the argument would be that there is nothing uncomputable in physics because you can always use nature to tell you the answer. But that just is not useful.
Yeah, not even that. Like, if it's computable, that means there's an experiment, and I think that's a bijection. I think if there's an experiment, that means it's computable. That's how I see it.
It depends
Like
on the definition of computability, right? I
Yeah,
mean,
but I think
there is a reasonable one, I guess, because if you want a physical computer,
exa Yeah, and I mean, you can imagine a computer with arbitrary add-ons. Like you can have a computer with a robot arm that manipulates stuff for you. So that's still a computer. So literally any physical system would fall under that, I think. If you can get the value as an output, that means it has to have been computable somehow.
Yeah, but the point is that you're putting the recipe of the construction of the computer outside the computability at that point. Because if you say that, let's say that the real number are technical real and implementable in physics, like those things actually exist, right? Then the infinite precision of where you put and your the physical value for the computer that you're constructing actually matter, right? Then you're basically saying that you are not going to be able to write the recipe for all the computers that you can build with finitely many simple infinite time.
Yeah.
And so you just move the problem of what the computer program is, right, to the construction of the computer. So yes, now your computers are all, they can all compute everything, but I have the halting problem on the constructor of the computers. So as I said, then I don't think it's interesting to say that everything that it's physically realizable is computable.
Yeah, no, in some ways it's not. It's just that like, I feel like it makes sense to rely on those sorts of mathematics that actually do fit that. That's where the whole argument comes in, right? Whether you want to be constructive or predicative or whatever. You want to be sure that you don't accidentally do something that wouldn't fit into this computability issue.
So again, going back, so if I am modeling a particular set I have a bunch of procedures in practice, and I can construct other procedure in practice.
Yes.
Then yes, I'm gonna have this. But the point is that the objects themselves that I am describing, they are not those procedures. So I have my physical procedure of testing to identify the objects, right? And those, yes, are going to have a requirement on something like computability, but it's not computability, it's experimental verification. But then the object themselves that I need to distinguish through experimental verification are the objects that I have in those particular cases. And I don't see any requirement on those objects to actually be computable function or computable anything.
I'm not sure I see the.
So let's put it like this, right? We talk about the computable reals, right? Okay.
Yes.
So whatever mass of the photon of the electron is, whatever it is, it's going to be by definition a computable real.
Yes.
The assumption, because I will have a machine that will spit out every digit and so on. Right? So it is not that when I look at the space of possible masses for the electron, I can limit myself to some type of computability of the reals, because whatever the mass of the electron is, even if it's uncomputable from some definition, it's going to be computable once I say there is the electron with that mass.
No, I don't think so. I think it's already it's going to be definitely a decidable real because you can set up an experiment that decides it, like, or at least semi-decide, like decide to arbitrary precision or
the
whatever.
experiment is going to give me a stream of essentially random
Of bits,
digits, one after the other. Right?
Yeah, but it's like a like the experiment itself is decidable.
Yeah,
or
but
at least
there
semi-decidable.
is no reason that I can predict what that number is.
I think you're talking about two things, right? The one is like I get the output, which is some position somewhere, and I need to be able to just even find out what the answer was. But what Gabriele was talking about is another map, which is just so decidable real means there is some computer program that, given my measurement data, can define what the real is in infinite time. But the map from some input to some output, that doesn't need to be computable, right? That depends on what you had to predict in the first place. So in our case, we don't have that much data to predict what the mass of the electron is. But if you think about initial to final state, there are non-computable functions from decidable reals to decidable reals. Then Mark is correct that, of course, in an experiment, it only makes sense to talk about decidable reals, but still the function from input to output doesn't need to be computable. Does that make sense? Or not?
To me, it does. I don't know if it makes sense to Mark.
Yeah.
I mean, sure.
So just to clarify, the possibility exists.
To me, it's like this. If it's an undecidable thing, then by definition, you'll never encounter it, because no measurement device could ever show you that value.
So no, let's think about it this way. Let's say, okay, it's a bit of an exotic world, but let's imagine there would actually be an oracle. We don't understand how it works, but it's an oracle that you can ask questions. The input will be a question, like a finite string, and you get an output, and you can definitely find out what the output is. It's just some answer. It's again a finite string. You cannot predict what the answer will be because it's an oracle, you know? But
Sure.
still, you had some process, namely asking an oracle that mapped an open set, which is a string to a string. So
I mean, yeah,
of course, the oracle, we don't know how it works. That's of course an exotic example, but does it make sense that those are two things? This is the fact that the oracle is not, I cannot predict what it's saying, has nothing to do with the input and output data being constructible, decidable.
The thing is, by having access to an oracle, you effectively extend the range of what's computable, because asking an oracle is also a function.
That's the problem. Like, you have a tautological definition here. It's not going to work. That's exactly what we're saying. Like, if you say everything that is that we can measure in practice is computable, then the theorem that tells us that there are some properties in solid state physics that you can't compute from the Lagrangian or whatever, it's you're saying no, that's not possible, because I can construct a computer by actually going and constructing the material and see what it is. But that's not that's not what they mean when they make that claim.
So I would have to know what example that is. There
there is a result that I looked at a few years ago, right? That basically there is a proof that there are some material properties that even if you know the material, you can describe the material and so on, you're not whether that material has that property is undecidable, right? That's basically that's the claim.
I guess that's one of the things in the quantum magazine, actually. Yeah.
Okay.
Yeah.
And if you say, but the property is measurable, because if it wasn't measurable, it wouldn't be interesting to say that the thing was not computable, right? Who cares if it's something not computable that I can't measure? It's not physics. But the interesting bit is that I can't use a general purpose computer with these inputs and outputs to go and compute that term.
Right. This doesn't quite make sense to me, just because a measurement is, in fact, a computation. So if you have a measurement that tells you, then it's already computable. It's actually sort of trivial in that way.
Right.
That's what he's saying, right? Gabriele, it's a circular definition. You
Yeah.
define what's computable by what is like physically doable. So of
Mhm.
course you can just do the thing in the lab and then you
Yeah.
just build the same experiment again in another room,
Yeah.
do it and use this as your prediction. Like if you just build the same experiment another time, hopefully you get the same thing if
The
you
same
done
result,
everything right.
exactly.
So in that
It should
sense,
be
it's
reproducible.
completely
Yeah.
circular, yes.
So that's not a useful definition, like as I was saying before. So the pi is computable,
Yeah,
regardless
for
of
sure.
what the mass of the electron is. We can compute pi. But
Mhm.
there is no need that we are going to be able to find an algorithm, right, that starts with just pure numbers and goes and calculates the mass of the electron. If that's not the
Okay,
case, right, then you can just
sure.
say this is the algorithm to calculate the mass of the electron, right? And then
Sure.
we would say that the mass of the electron is not computable. Of course, we can go and measure it, right? But that's
Yeah,
it, right?
it's just I feel like that's like okay, you can't have a function from the set of real numbers to the mass of the electron, I guess. But that's
Right.
that's like starting from the wrong starting point because that's not how you calculate mass in the first place.
Well, that would be the point, right? So to say that I had that the mass of the electron were calculable would
Mhm.
basically mean that I have a procedure implemented with the Turing machine, right? That takes
Mhm.
no input. It has a finite computer program and starts spitting out the electron one after the other. And when I
And,
measure them, they are correct. And there is no guarantee that such a thing exists. I don't see why it should be exist.
as I no, the thing is, a Turing machine is a really abstract thing that can be so many things in real life. Like, yes, it does exist because you can have well, semi-decidable. It's really just semi-decidable because you can never have the infinite, whatever. It's you can have because
No,
a
look,
real life
a
machine
computer
is a Turing machine.
a computer machine has a finite program. Okay,
Well, finitely readable, I guess. Yeah, sure.
it is a finite program. So there are in the limit you can have countably many. That's as much as
Mhm.
computing
Because
Turing machine you can have.
you
Do you
could
agree with that?
I think you could technically find stuff like repetitive Turing machine band or something where it's technically infinite but finitely like describable because you can say, okay, after so much it repeats again, right? That's still a valid computer program.
Okay, what's the countability of the class of Turing machine? Is it countable or is it is the continuum?
I don't know that, but I mean it's a function from effectively if you take a single Turing band as the digits of an integer or something, then it would be a map from integers to integers, which I think is effectively a continuum, right?
No, maps from integers to integers.
You would have infinitely many digits.
That's like you can
You
have
assign to
the
each position in
You
your
can't you
digit
can't get
expansion.
all the maps. I mean, as I said, we are also restricting with the fact that we're not even have an input, right? So it's just going to be a Turing machine that starts spitting out numbers, right?
would it not have an input per definition? But
And it has a finite program, okay? And since it has a finite program, it will always, you're guaranteed to hit the same state at some point.
Mm.
And therefore, you're gonna only be able to give me something that it's irrational because at some point it has to start repeating.
No. So irrationals are definitely not, they are constructed, like you can very easily construct a square root of 2 or something. A Turing machine can absolutely calculate a square root to arbitrary
Okay, so
precision.
I need a state. Okay, then the state needs to be infinite. Otherwise, so it's not a finite state machine. Correct. Yes. If it would be a finite state machine, you basically
Yeah,
you are
Parallel,
too restricted. Okay. So the argument that I said, it's not true, that applies only to finite state machine, but still, so the point is that, can you spit out every... No, because again, the choice of the program is going to determine what is going to be the output.
It's just like defining a procedure in a lab and
Yeah, I think
measurement
we're
of
going nowhere, and we already like hit 2 hours.
Yes.
want
Sorry,
to
it's just yeah. I
stop.
don't
But
think yeah.
so I still, so the point that I'm trying to make is this: what we mean by computable for something like the mass of the electron is not the fact that I can go and physically realize a computer that just measures the mass of the electron. I don't think that's a useful definition for physics. What we
Okay.
mean is that we can use a general purpose machine and write a program on a general purpose machine, and the output of that program is going to match, is going to predict what the mass of the electron is.
But why is a general purpose machine not arbitrary lab experiment? Like that is a general purpose machine.
No, it's not a generic purpose machine. It's a machine that I built specifically to measure the mass of the electron, and it has the electron as an input. It's not
Okay.
a general purpose.
Right. That's why it's more restricted than a Turing machine actually in that case, because it only does that one
You
thing.
can only compute that thing, yes.
Yeah. Okay.
And the
Yeah.
same
Still.
thing if I would implement, my particle accelerator prediction with a particle accelerator. It's a very specific machine. It's not a general purpose machine.
So you can describe on a Turing machine the way to get to that other machine, and then
I don't know if you can. I don't know if you can, right?
I
Like you
see
need
no
different
reason why you
hardware.
couldn't.
Like you need the electron. You need different hardware to be able to do it. It's not just ands and ors and not gates. I have a gate that is it's an oracle. Go and measure the mass of the electron with this precision. It's from the perspective of if I'm writing my computer program, I will have an external function that calls the experiment and it gives me something. It's an oracle from the perspective of the computer program.
Yeah, I'm not so sure about that. Okay.
Yeah. I wouldn't know how to implement that with ands and ors and gates, and so it's
Yeah. I mean, sure, but
okay. So I think that's the
yeah. We're talking like functions are more general than ands and ors. Like you can prove that those are enough to get a Turing machine, but you could have different components in a Turing machine in principle. But yeah.
Doesn't
okay.
really make sense to say that if we would build in from the start computability in everything we do, then this notion of computability used in mathematics relies on a usual Turing machine, right? That's what they did mean by computable, I guess.
Sure.
Yeah.
And then you're saying if we would find physics that is not computable, that is basically means we have physics. We could build something stronger than computable. We
Right.
could build an oracle, and then we would have a different notion of computable, stronger than the one used in mathematics.
Yeah.
And that
Yeah, I just don't
just
think that exists.
unreasonable, of
Yeah,
course.
which is exactly what we did with the extension of quantum computers, right? So there is classical computability, and you can do a certain class of problems, and then people realize actually quantum mechanics can do more things, and so now you have a certain extension, and you have some problems that were not solvable in the domain of classical computation that are NP complete in terms of classical computation that become
Yeah, but that's a different thing. NP complete does not mean it's impossible. It just takes a really, really long time.
Fair
We're
enough.
talking literally impossible. The quantum computer is not more powerful than a regular classical
Fair enough.
computer.
Yes, I agreed. Yes.
Yeah, that was about how fast it is, right? Okay, but anyway, so basically,
So it's not exactly,
just
but it's similar. We're talking about similar, like something
yeah,
that
that's
is
true.
not.
Okay, but so in the actual sense of computable at all, in however slow it is. So if that would happen, we would just find, okay, actually physics allows more computations. you would update our notion of computability, and then just by definition, everything will be computable again, trivially. So if we would now actually, like, starting next week, just use computable mathematics, then we would already have decided we only look at physics that can reproduce Turing machines and nothing else. So this is actually already in a restriction, which might not be a strong one, because we don't know any crazy physics that can, build super cool computers. So it kind of I guess we expect to get away with it, because we just want to recreate normal physics, but we don't have a priori a reason to believe the Church-Turing hypothesis that there is nothing stronger, right? So we can just do it. We probably want to know that stuff is still computable that we use. But yeah, it's really the axioms, like, somehow like really reference what we mean by a Turing machine, right? It's not with the new computability model, the axioms would be different ones, right?
Yeah, you limit yourself mostly to a subset of the classical ones. Sometimes you might use different ones, but for the most part, no, it's just a limitation. You strike some axioms and say, I have to rely on only those.
Okay.
Well, and again, to reinforce what Tobias was saying, I do not want to impose any computability restriction to the functions that the nature provides us, because I do not know what is the computational model on which that thing works. So I need to be open to accept anything as long as it's something that I can physically identify. If I can't identify it physically, I can tell it apart from, experimentally, then okay, I'm not gonna care. That's true.
Yeah, it's kind of the opposite though. If you restrict yourself to fewer axioms, you arrive at a theory that's valid in more situations. Like, it's not like the classical stuff suddenly becomes invalid in that case, especially if you only restrict and don't go to a theory where it's like the opposite.
We are saying that restricting ourselves to the assumption that the functions that nature provides are computable in some computable class is the more restricting assumption, is adding another axiom.
No, it's not. It's
Yes.
striking axioms. I suppose it's that notion is incompatible with some of the axioms in classical mechanics, and you're adding one and striking a few others. And in total, it's still.
Are we agreeing at least to what you're saying, or what we're saying? Because maybe it's just a word dispute. Tobias, do you understand what I said? Can you repeat it to me and see if it was intelligible or not?
So I get the same problem. I always it's another axiom. It's stronger, but actually, I get confused. Can we do more or less? I understand why this could be confusing. What you said, I would agree, is if I restrict myself to computability, to a certain type of computability, I of course exclude that I will find an oracle in nature, right? So I will restrain myself. Like, if an oracle pops up, I couldn't model it. If I just don't assume computability, then it could just be there. It probably won't, but it could.
Okay.
So that's not even.
Does that make
that
sense?
limitation is not even true. You can absolutely assume that an axiom exists, an oracle exists. You just say, if this exists, then I can show that. But you just don't presume from the outset, and you definitely have an oracle that can decide the halting problem.
Mark, I'm not following. Do you understand what Tobias repeated about what I said? Because I think Tobias did the same characterization that I did. So do you understand that? You understand the claim that if we say that nature has to follow a particular type of computability, then we're restricting ourselves to the physical theory that only can describe that type of computability. Do you understand the claim?
Yeah, but I don't think it's a correct claim.
Okay, so what exactly in that claim
Wait.
is
So
wrong? Because
That's
I
what
don't.
I just said. You can always assume that an oracle exists and then see what happens from that.
There was no claim about Oracle. I'm just saying, if I restrict myself to a certain type of computability, then I have only the theories that computability allows.
Right. It's
Right.
just that
So it's a
within
restriction.
I think
that,
we're confusing. We're going both ways. Restricting computability means I don't want to include axioms. Like I have less axioms to work with, right? Sorry, isn't that what you're
yeah,
doing? So
yeah.
I think we are going two ways. So
No, to define computability, I have to define a computing device and I have to define a computable model. Because on that
Sure.
model, I will say what I can compute and what I cannot
And
compute.
within that computable model, you have whatever basic constructions are accessible to you, which could include stuff like a more powerful thing that allows you to compute extra things.
Right. So I do not know what is the computability of the universe, right? I don't know what is the computable model. So I have to be a completely agnostic, and so I cannot even be. I shouldn't be able to talk about what is the computable model of the universe because it's something that I have to experimentally find.
Sure.
And then you can say, well, whatever computable model the universe has, so that's going to be defined as computable, which I don't think so, because it's not just a matter of what the universe can provide, but what we as finite human beings can provide, which is certainly less, and it's not going to be more. It can be at most equal, but probably it's going to be less than what the universe can do.
Yeah, I don't think so, but even with
I don't think so. Like I'm making a point, like 1, 2, 3. So either is something wrong or there isn't something wrong. So
no, I really do think that measurable means computable. That is really a thing that I believe.
yeah, we
But
already discussed that this to us is a tautological definition.
it's not to me though.
I understand that it's not to you, but it's to us it's a tautological
yeah, I
definition.
know.
Like it's not
The thing is, you
useful.
can always add in extra premises. They wouldn't be axioms. You just have an extra assumption for that one statement once and say, okay, in this instance, I have access to that. And then suddenly it works. So it's not really a restriction in that sense.
Like
So
look, I need to boil it down to see to sort of a simple premises. The premise that everything that it's physically resolvable is computable, right? And so everything is everything that exists is computable is not useful. And even in the literature of when people discuss this computability problem in physics, they don't talk about it in that term because otherwise everything would be computable. And by definition, there wouldn't be a question of asking whether a physical theory is computable or not.
Sure. I mean, you can.
So it's not a
You can
useful
ask that question,
definition.
yeah.
The useful definition that I have intuitively is what I said before. I can use a general purpose computer and I can write a program implemented by using the physical laws that we have written to go and find problems. And then there are some problems that are not computability, like chaos and so on, dependence on the initial condition, and people address them in some ways, but even there are limitations of what you can do. And then there are the real computability problem. But the computability problem is still has to be separate because otherwise there is no problem to discuss. Everything is computable.
that makes sense to me.
Okay.
So if you're fine, we're saying, well, everything we do is computable and that's it, and I don't see a distinguisher. The distinguisher is not useful to me. That's fine. You can have that position, but me and Tobias and probably other people are going to say, well, we want different definitions so that we can talk about this stuff. So. Okay, you can't impose on me a definition that I don't think is useful.
No, absolutely.
So that I can't talk about the
You are
things that I
not
think.
obliged to use anything I
I
say.
think
That's obviously true.
I'm also a bit confused about because so I understand that for example we can just not use the axiom of choice as long as we want. There is no harm in not using it. In case we need it, we just use it, In that sense, we can't do anything wrong. in a sense, but just using less axioms for as long as possible. I think that's kind of where what is confusing.
Right, but here's so if I'm asking, I have one to fewer axiom to run my mathematical proofs, that's fine, but that's not. So it's the issue of computability in the theory, on the physical proofs and so on. It's completely separate, like I keep repeating, with the fact of whether the physical objects are one way or another.
Yeah.
Right?
Yeah, absolutely.
And so after this discussion, I'm more and more convinced that probably it's better just to keep those things separate so that there is no confusion. Because if we start saying, oh, we want to use, our definition of experimental verifiability, we want to merge it with with the definition of computability and all the other stuff at the foundation of mathematics, then I think it's more territory where the mathematician might get confused that there is only one definition and it's the same, and so it makes a weird mixture. And the physicist sort of does the same on the other side. It thinks that everything that that it has, the definition that you use for physics is the same for the other side, and then nobody understands anything of what's going on.
Yeah.
Like as a practical sociological thing. So if you keep the two issues separate, even in the notation in the math, people are not going to get confused, and you use different terms.
Sure, I mean that's fine. Being more specific with notation is probably rarely an issue, a mistake.
So how do but I don't understand. So the axiom of choice, for example, assumes the existence of certain objects.
Yes.
So in that sense, not using it. So using it means I have more objects. Right?
Fewer in a way because it collapses and stuff.
That's the thing
yeah,
that
okay.
where maybe the confusion comes from, because sometimes you have more, sometimes you have less.
No. So for me, it's completely clear because I've done I see that physicists always struggle with this. Mathematicians and people that come from computer science don't struggle. So if you want a general definition, okay, a general definition is built on fewer premises.
Yes.
Yeah.
Okay, so if I have a collection, right? A
Yeah.
collection is just something that I can ask whether an element is in a collection.
Sorry, say again?
Set, yeah.
A collection is an object that I can ask, is this element in the collection?
It's the element relation is the only thing in set theory. Yes.
Okay. So now, and that's the only thing, let's say, that a collection does. Now, if I want a list is a collection, right? I can ask whether the element is in the list.
Yeah.
But it's an order collection. So there will be a function that I give you the number of the element and you give me the element at that position, right?
Yeah, you get
now
indices.
That can do more, but it's more restrictive because
Yes.
now a set is not a list, though a set is a collection.
You trade generality for structure.
So wait, so you now have more
you have more features. Like you can ask the object more things. You can ask, give me the element at the third position.
Okay.
Right? So it has more functionality, but it's less general because there are collections for which you cannot ask what is the element at the third position because those collections are not ordered.
Yep. The order relation is an extra.
Let him sink in because
it doesn't really make sense to say there are no more sets when you include the axiom of choice.
There are fewer sets because there are some sets in which you can ask, give me what's it called? Give me the choice function. Right? So you have a set. Now the set is going to have a function that tells me, okay, is this element there? Okay, right? And now I have sets with choice, which are sets that can do everything that the set does, but also they can give you a choice function.
So in a sense, I'm restricting myself to sets where, what was the choice function again? Just given some predicative or something, it can select an element or something like this.
Yeah, you can give you
Okay,
an
so you
element from there.
so in that sense, you're restricting yourself to sets that only have this, but it looks to me maybe it's stronger. There are more, but I mean, because essentially in this context now, the other sets where I don't have these functions, I just don't consider them. Like I say they don't
But
exist.
what you have is it's fewer sets, but those sets you have more statements that you
More
can prove
structure.
about them.
Okay, I
More
think we lost
statements so
the
that
stream
provable,
somehow. The
but
stream
fewer
broke.
sets.
So
Okay.
I'm gonna end it because it corrupted. I don't know what happened. So
Oh,
Okay.
okay.
vabbè, quindi it's just between us. Let's put